Welcome to this explainer. Okay, let's dive right into this fascinating geometry tool belt and see exactly how simple rules built complex shapes. Now, if you are sitting down for a Cambridge mathematics paper, whether that is the 0580, the 0606, the 4024, the 4037, or even the 4040 syllabus, you need to approach it like a chess grandmaster. You cannot just react to the paper. You have to think 5 moves ahead and anticipate the examiner's next mental move. Today, we are going to unpack the foundational principles of geometry, taking information straight from the source material to reveal the underlying logic of the spaces, angles, and shapes all around us. We'll look at where students typically lose marks and how you can secure them. Let's get started.
Our roadmap today covers 5 absolutely crucial areas. This is essentially the examiner's hit list. We're looking at symmetry and measurement, navigating with bearings, core angle properties, parallel lines, and finally, polygons and tessellations. Master these 5 pillars, and you'll be practically bulletproof when it comes to the geometry section of your exam.
Section 1. Symmetry and Measurement. We're beginning our journey by looking at the very foundation of 3D shapes and exactly how we quantify their angles.
So here on the screen are your classic three-dimensional shapes. We've got the cuboid, various prisms like the equilateral triangular prism, the right square-based pyramid, cylinders, cones, spheres, and of course, the cube. Now what's really fascinating and what the examiner loves to test is that these aren't just arbitrary objects. For every single one of these shapes, we can determine something called the order of rotational symmetry. This is a measure of how many times a shape looks exactly the same as it rotates around a central axis. I see a lot of students, let's call hypothetical student Alex. Alex overloads on raw mathematics facts. Alex memorizes the names of all these shapes but completely fails to analyze how they move in space. When the exam asks for the order of rotational symmetry of a right square-based pyramid, Alex freezes. But if you visualize that shape spinning on a table, you can see the mathematical perfection. You can see how many times it locks back into its identical footprint in one full turn. That is the grandmaster level of visualization you need.
Now, when it is time to actually measure the angles of those shapes, we use a protractor. And following these precise steps ensures you never read the wrong scale. I cannot tell you how many marks are lost right here. Let's imagine another student, Sam. Sam is smart, but Sam rushes. Sam completely misses the command word requirements and just slaps the protractor down. Don't be like Sam. First, you place the cross right on the vertex where the arms meet. Then, you perfectly align the 0-degree mark with one of those arms. Step 3 is where the trap is set. You must make a crucial decision between the inner or outer scale. You always choose the scale that starts at 0 for the arm you've aligned with. If you use the inner scale when you should have used the outer, a 30-degree angle suddenly becomes 150 degrees and you've lost the mark. By carefully following this 4-step method, you quantify the exact degree of turn and secure that point.
Section 2. Navigating with bearings. This is where we take our tools into real-world geometry. This is a huge area for exam questions.
Look at how this concept actually evolved over time. In the early days of sailing ships, navigators just relied on the simple cardinal points, north, south, east, and west. But as ships needed to hit more precise targets across massive oceans, this had to expand to 16 points. That introduced directions like north-northeast. Then, as the need for accuracy grew even more, it went all the way up to a dizzying 64 points. Can you imagine trying to shout that out in the middle of a storm? No way. So, as travel speeds increased throughout history, especially with aircraft and modern ships, navigation had to completely evolve from simple compass points into a highly accurate, unified mathematical system. That's what we use today.
Before we continue, subscribe to our YouTube channel, Ace the Exams at acetheexams_IGCSE to excel in your Cambridge examinations. Click that subscribe button and hit the bell icon right now. Okay, so that historical evolution led us straight to modern bearings. The crucial thing you absolutely must remember for your exams is that modern bearings are always measured in a very strict, specific way. North is always set as absolute 0. From there, you measure a full 360-degree rotation strictly in a clockwise direction, never counterclockwise. And here's the golden rule that examiners will penalize you for if you forget. It is always written as a 3-digit number. If your angle is 45 degrees, you cannot just write 45. You must write 045 degrees. If you write 45, the examiner knows you don't fully grasp the system, and you drop the mark.
Let's test this tool out. This is a classic high-frequency exam scenario. If you were tracking a point backwards, what we call calculating a back bearing, how do you actually do it?
Imagine you've traveled from point A to point B on a bearing of 245 degrees. If you suddenly need to turn around and look straight back at your starting point A, what exact bearing are you facing? Take a second to think about the mental move here.
The answer is 065 degrees, and again, notice the 0 at the front. But let's break down exactly why that is. Because memorizing the answer won't help you on the day. You need to understand the underlying logic.
It all comes down to parallel lines. A north line drawn at point A and a north line drawn at point B are perfectly parallel to each other. Because of this structural fact, if your forward bearing is over a half circle, like our 245 degrees, you simply subtract a straight line, which is 180 degrees, from it. 245 minus 180 gives us 65, and because it's a bearing, we format it as a perfect 065-degree back bearing. It's a beautifully simple calculation once you mentally visualize those parallel north lines pushing up towards the top of the page.
Stop scrolling. Subscribe to our YouTube channel, Ace the Exams, at Ace the Exams IGCS to excel in your Cambridge examinations. We've helped thousands of students improve by 2 to 3 grade boundaries. Join them right now by subscribing to at Ace the Exams IGCS and turn on all notifications so you never miss our weekly exam strategy sessions. All right, let's move into Section 3 Core Angle Properties. These are the fundamental laws of geometry.
This table brilliantly illustrates our core logic in the simplest terms possible. If you stand at a point and turn all the way around until you face your starting direction, all the angles around that central point will add up to exactly 360 degrees, a complete circle. Conversely, if you have angles sitting along a perfectly straight line, they are making exactly half of a turn. Therefore, they will always, without fail, add up to 180 degrees. These are your non-negotiables. When you are looking at a messy, complicated diagram in Section B of your paper, you need to actively scan for straight lines and complete circles. That's your anchor.
Let's see that straight line rule in action. Imagine a straight line split into 2 angles. One angle is a complete mystery. Let's just call it x. The other is given as 130 degrees. Because of our golden rule, we know they must combine to equal 180. The math is simple. If you have an angle of 130 degrees on a straight line, the missing angle simply has to be 50 degrees to complete the 180-degree rule. It's literally like a geometric puzzle where you always know what the final picture is supposed to look like. The examiner is just hiding one piece from you.
Moving on to Section 4, Parallel Lines. This is where we look at intersecting systems, and this is typically where the difficulty ramps up in the exam papers.
First up, imagine 2 straight lines crossing each other, kind of like an open pair of scissors. This intersection creates what we call vertically opposite angles. Because angles on a straight line always add up to 180 degrees, it naturally guarantees that vertically opposite angles will always equal each other. Think about the symmetry of it. If the top angle of the scissor opening is 40 degrees, the bottom angle is exactly 40 degrees. They mirror each other perfectly. Whenever you see an X shape in a diagram, immediately identify your vertically opposite angles.
Now let's draw a straight line right through 2 parallel lines. This intersecting line is called a transversal, and it creates a whole complex system of matching angles. When a transversal intersects parallel lines, you need to look for visual shortcuts. You are scanning the data just like a grandmaster scans the board. First, look for the F formation. This shape highlights your corresponding angles, which are situated in the exact same corner at each intersection and are perfectly equal to each other. Then shift your vision and look for the Z formation. The Z shape highlights your alternate angles. These are tucked on opposite sides of the intersecting line, right between the parallel lines, and these two are perfectly equal. If you can train your eyes to instantly spot the F and the Z, you will fly through these questions.
Meanwhile, there is another pair we need to watch out for, and this is where a lot of students trip up: co-interior angles. These act a bit differently than the F and Z angles. Co-interior angles are the ones that face directly at each other, inside the parallel lines, on the same side of the intersecting line. The trap here is thinking they are equal. They aren't equal to each other. Rather, they are supplementary. This means they work together to add up to exactly 180 degrees. If you know one is 100 degrees, you instantly know the other is 80 degrees. Always check if you are dealing with an equal pair or a supplementary pair.
Section 5. Polygons and tessellations. This is our final tool, looking at how straight lines enclose spaces to build complex shapes.
Let's start with a really clear definition so we are all on the same page. A polygon is simply a closed, two-dimensional shape made entirely of straight lines. You need at least 3 lines to enclose a space, which of course makes the triangle our most basic polygon. From there, we build up to quadrilaterals, pentagons, hexagons, octagons, and well beyond. And understanding the angles hidden inside and outside these polygons unlocks a truly fascinating property of geometry that examiners love to bring up in the final high-mark questions of the paper.
Because of their specific, highly mathematical angle properties, certain polygons can do something amazing. They can tessellate. Tessellating means they fit together side by side perfectly, creating infinite patterns without leaving a single gap or overlapping by even a fraction of a degree. Think of a honeycomb in nature or a beautifully tiled floor. This is only physically possible because the angles at the exact points where the shapes meet all add up perfectly to 360 degrees. If they added up to 359, there would be a gap. If they added up to 361, they would overlap. It has to be perfect.
Now, here is a brilliant way to visualize the rules governing these shapes. Imagine standing right at the corner or the vertex of any polygon, let's say a pentagon. Start walking along the edge in a clockwise direction. Every time you hit a corner, you have to pivot and turn to walk down the next edge. The exact angle of that turn you just made is called the exterior angle. Here is the magic. If you mentally walk the entire perimeter of any convex polygon and turn at each exterior angle, by the time you return to your starting point, you will have turned exactly 360 degrees. It does not matter if it is a simple triangle or a massive shape with 100 sides. The sum of those outside turns is always a perfect 360-degree circle. It's one of the most reliable rules in all of mathematics.
We've built our tool belt from simple measurement and bearings all the way up to the infinite patterns of tessellating polygons. You now have the exact blueprint and formulas to decode the hidden math around you, and more importantly, to anticipate exactly what the Cambridge examiner is looking for. Students who implement these mathematics strategies see an average improvement of 2 grade boundaries, but only if they practice consistently with our weekly videos. Here's your final reminder. Subscribe to our YouTube channel, Ace the Exams, at acetheexams_IGCSE to excel in your Cambridge examinations. Subscribe right now to @theacetheexams_IGCSE and click that bell. Don't let another exam pass you by. Drop a comment below with your target grade for mathematics and the biggest challenge you're facing. Our team responds to every comment. Like and share this video with a study partner. Ace the Exams. Your Cambridge success starts here. Keep observing, keep calculating, and I will see you in the next strategy session.